Now, we will go into multidimensional integral. What we will do is we will evaluate this 6 dimensional integral. So, where basically x and y here are vectors. So, it has 3 components, each has 3 components x and y. So, the total the integral the dimension of this integral is 6, and we will evaluate this particular integral, and we will use it use two Monte Carlo methods. One is the brute force one, which is the simple Monte Carlo technique, and then we will use what is called the importance sampling, which is a improved and more efficient way of evaluating these integrals using Monte Carlo method. So, let us first look into the brute force way. So, this is my file multi-dimension brute underscore F90. So, this is the program which will do the brute force integral for us, and the idea is exactly same as the previous examples which we looked for Monte Carlo integration, for example, e to the power integration of the e to the power x, but there we had only one variable x. Here we have 6 variables. So, x1, x2, x3, x4, x5 and x6. So, for that what we need is 6 random numbers instead of just one random number, and this volume will be a 7 dimensional volume. That is the value of the integral which we will get. And so, though I mean the limits of this integral are from, sorry, there is a mistake here, this will be from minus infinity to plus infinity, but we can't do that on a computer. So, we will restrict the limits to minus 5 to plus 5, and this is a very valid assumption, because this function, as you can see, it is a form of a typically form of a Gaussian, which decays exponentially e to the power minus x square of, that is our rate, that is how it decays. So, it decays very fast. So, it has a long tail which will have negligible contribution to the integral. So, let us see how it is done. So, by length, that is here, instead of the complete length of the integral, I have used just one side from 0 to the positive x1, for example, or 0 to positive x2 or 0 to positive x3. So, the total length along each dimension, say for x1, the total length is twice this value, that is 10, we have 2 into length, and since this is a 6 dimensional integral, so the volume will be given by to the power 6. So, this is my volume. I need to multiply the average of the function with this volume to obtain the integral. So, now I start computing again, as before I will be doing it for several values of n. I will be evaluating, say, the integral using 10 by computing the average 10 times, then 100 times, 1000 times, so on and so forth, and we will see how the number accuracy is changing. So, what and those values are stored in this particular file here. Then I ask the user to give me a small value, the starting value, then I initiate my variables to 0. This one stores the final value of the integral, this one stores the variance, and this one stores the sigma. Then what I do is, this is the place where I am executing this do loop helps me in computing the average. So, each time this do loop is executed, what it does is it calls a 6 random numbers. So, now unlike the previous cases, here you see this p argument which is used which is a dummy argument for my random number generator, it has a dimension 6. So, what it means is that it will return 6 random numbers, and once I got these 6 random numbers. So, what I need to do is, these random numbers are 0 to 1, and again as before, now I need to have these random numbers spaced from minus 5 to plus 5, and this is how that is done. So, the p's I am converting to p's which lie between 0 to 1, I am now here is converting it from minus 5 to plus 5, and once I have that value of p, I call this function. So, this function does nothing but evaluate the integrand. So, basically this is what it does, e to the power minus a x square minus a y square minus b x y, where a and b are 1 0.0 and 0.5. So, it is nothing but just basically this particular function. So, if you compare this with this thing, yeah. So, this is the function it is trying to evaluate here. So, this is e to the power minus x square minus y square. So, my x square will be x, the x component x 1, x 2, x 3, that the mod of that vector, and then that is what is here, the x square, x 1 square plus x 2 square plus x 3 square. Similarly, y square will be given by x 4 square, x 5 square and x 6 square, and then I have x minus y whole square. So, this is how the function is evaluated, and once I get the value of the function at a given set of values of x, I add it to this this particular variable, and I keep on doing it 10 times. Similarly, for the same way I do for the sigma, and once that is done. So, for the integral, what I do is I compute the average, and once the average is computed, then I compute the I multiply it by volume to get the value of the integrand. So, once that is done, what I do is I write my n, then the value of the integrand, and then the standard deviation. So, this I print into the file, and this is done till a certain number of n takes a certain value. Okay. So, this is how it is done, and then let us see how efficient or how it performs. So, I compile it as before. Dimensional mult dim underscore brute f90. So, if I compile it, then this is the executable that has been produced here, you can see. Then I run it. So, it asks for a value of 10. I start with a ridiculously small value, though it is meaningless, but let us start with that. And so, the code is now doing the calculations. So, let us wait for some time for it to finish the calculation, and then we will see how the results are. So, particularly the last 2 points take a significant amount of time. So, that is why it is so it is still doing okay, it is done. So, now if I do ls minus ltr, so what I see is that this is the file where I have my data which is generated by the code. So, if I grep that out, so I get the following. So, again just a reminder. So, this is the value of n, that is the number of random points I use to compute the average of my function. This is the value of the integral, and this is the standard deviation. Okay. So, what you see is that so for example, with 10 grid points random numbers or with 100 random numbers, you get some ridiculous values of the integral. It is completely wrong, you see, and to get somewhere close to the very small. So, in Monte Carlo integration, the accuracy of the integral typically is determined by the standard deviation here, and you see that even with so many points, with these many points also, the standard deviation is still pretty high, which you do not want. You want a very low standard deviation. The lower the value is, the more accurate will be your calculations. So, now to improve this, what we will do is we will use the we will evaluate the same integral here using this importance sampling. So, if just to recollect what importance sampling is what we do in importance sampling is we modify the function in such a way that, or in other words, in importance sampling, what we do is we have a distribution of random numbers which has a uniform distribution. We change the distribution in such a way that the shape of the distribution matches the shape of the function. So, for example, here this function is sort of like a Gaussian function. So, what we will do is we will do a change to two things. One is we will change the random number generator which gives us a uniform distribution. We will use that random number generator, generate a set of random numbers with uniform distribution and change the distribution to that of a Gaussian deviate. And once it is done, we will also do another thing, that is the change of the variables. So, when we do the change of the variables, that is basically what it means is we will divide this function by e to the power minus x square and minus y square, that way. So, once we divide this by that function, so what will happen is these two terms will go away. So, my modified function will just be the exponential minus x minus y whole square. Okay. So, this is what, so I have to integrate this new function with a distribution of random numbers, which has a Gaussian distribution now instead of a uniform distribution. And the way we have also learned that how to generate a Gaussian distribution. For a Gaussian, to generate a Gaussian distribution, what we need is two random numbers at a with uniform distribution at a given time, and then we will use the Box-Muller method to do that. So, let us look at how the code is. So, we go, so this method is called the importance sampling. This is what my program does. So, again as before, I have a set of integer variables which are used for the same purpose. Here I have one more extra counter. Then again I need 6, basically I will be needing 6 numbers. So, that is stored in this variable x, and each time I need 2 for each number, a random number with Gaussian distribution, I need 2 numbers with from the uniform distribution, which are stored in this variable p 2. Okay. And then I have this particular function which generates my Gaussian distribution, random numbers with Gaussian distribution, and this is the function which evaluates the value of the integrand at those set of 6 numbers. So, again this length is given by this. Now, if you do the algebra, your volume, you have to multiply it by a factor of pi cube. So, this is what is given here, and in the Box-Muller method, the standard deviation of my Gaussian distribution is different from the standard deviation of the Gaussian distribution we need to use. So, and if one does the algebra, as we have seen before in the lecture, so we need to multiply this or divide the number by square root 2. So, this is what, and since we need to do it every time, so instead of evaluating this every time, we evaluate it in the very beginning and store it in this variable. And then we, as before, we write the values of my integral and the error in this file for different values of n. We ask the user to supply us the starting value of n, and then I read that same thing. Then I set my different variables to 0, and then I start doing the average. So, basically what I am doing here is I am doing the average, the first loop. So, unlike before, now I have 2 do loops. So, this is the first loop here, starting with do I equals to 1 to n, and it ends here. And then I have the second do loop. What it does is it generates 6 random numbers with a Gaussian distribution starting from. So, what I am doing here is I am calling my random number generator to return me 2 random numbers with uniform distribution. These 2 random numbers I am giving as an input to my function Gaussian underscore dev, and that returns me one random number with which forms a uniform Gaussian distribution, and that I am multiplied by square root of 2. So, that my sigma of the Gaussian distribution remains the same as I desire to do my integration, and not the original Box-Muller sigma for the original Box-Muller. And once I have these 6 numbers here through this do loop, what I do is I feed them to my function. The function is evaluated using this particular function here. So, this is the function where I am evaluating it. So, now you see the function is just minus half x y. So, only that part is left. So, once this function is evaluated here, so what I do is I compute the average in this line, Then similar way I compute the sigma by computing the average, then I compute the variance, and then what I do is I multiply it by the factor of pi whole cube and the sigma also by volume and then square root of n, and then I print them out in the file. So, this is how it is how the code works. So, let us see, let us now try to run it and see what happens. So, first, but before running it, we need to compile it gfortran minus o mult and then underscore imp x Monte Carlo dot F90. So, again if we do ls minus ltr. So, I have this particular executable file which I will use to run my code. So, I start again with a ridiculously small value of 10. So, it is running and we will soon. So, one thing we should remember is in most cases in Monte Carlo simulations, you will not be able to evaluate the exact value of the integral, and that is precisely the purpose why you are using these methods. So, in those cases the error is basically given by the value of the sigma. So, the smaller the value of sigma, the more better is the estimate of the error, unlike in other grid based methods, where sometimes you might be able to know the value of the integral exactly. So, this takes some time here, and so let us wait and hopefully it will be done soon. So, it is doing for several values of n, starting from n equals to 10, then 100, 1000, 10,000, 1 lakh, 1 million and so on. It goes I think till 10 to the power 9. So, that is why it is taking such a long time, but yeah, let us wait for some time and it will be, hopefully it is done soon. Let us see how much it is done. It is still running. If you use the top command in your Linux machine, those who are new to Linux, then you can see what job is running. So, as you can see, this is, it is still running here. Let me close this. It's still doing something. It's so it is taking time because okay, it's done, but because it's now we are doing an extra step, that is, it is generating a new distribution of random numbers. So, that way it's a bit expensive. So, once it's done, then what we do is, so this is the file which has been produced where the data is stored, and let us look at it. So, imp dat. Okay. So, again this is the first column is my n, the second column is the value of the integral, and the third column is the sigma. So, as we see, and let us compare this with the brute force one which we did in the previous thing. So, if we see that in the brute force one, the lowest value of the sigma that we can get is 0.11, which is just 1 order of magnitude smaller than the value of the integral. For the same number of points here and here, now with my importance sampling, you see it is converging very fast, the sigma is decreasing very fast. And if you do the algebra, you can see that the sigma will go as sigma 1 by square root of n. That also you can check and see whether it is valid. So, this is a clear example that in doing this type of integrals, the importance sampling, though it might be slightly expensive than the brute force method, performs or gives a much more accurate estimate of the value of the integral. So, we will see how to test the random number. So, what I will take you through a code which has been written by me, which what it does is it does the different steps of the random number. So, in the lectures what I have told is, so we have to check whether one gets the expected value of average value, the expected value of sigma, then the correlation plot one should do the scatter plot, one should do the histogram. So, these are the 5 tests one needs to do. So, I will not go into the histogram, I will not show you how to do the histogram, but I will show a code which does the other stuff. For so example, this is my code test random number dot f90. So, I start with the Fortran keyword program, and then I have the program name, and then I have a set of variables here. It is a long list of variables. Some of them are temporary variables which are used in the code, and others are the significant ones I have within comments I have kept here what it means. For example, average AVG variable stores the mean of my distribution, sigma variable stores the standard deviation, C underscore k stores the autocorrelation, and these are some again dummy variables. So, to begin with, I make it 0, I set the sum 1 and square of sum to be 0. So, what I will do is, so I need to have 2 files. One file will store my correlation coefficient, which we have defined already in the lecture as a function of k, and in the other one I will store x1 and x2. That I mean the basically what I am going to do is I am going to store the data for the scatter plot. Then in this part what I am doing is I am asking the user to tell me how many random numbers I want to use, and then I read that number. So, this particular section what it does is it will compute for me the average and the standard deviation. So, what it does is it will this first do loop what it will do is it will call the random numbers n random numbers that depends on the value of n, and these random numbers I sum them up and store in this variable, and then I also take the square of the random numbers and sum them up and stored in this variable. Once that is done, what I do is the average is computed by dividing the number stored in sum 1 by the number of times or the number of random numbers I use, that is n, and then similarly I compute the average of the square sum, that is given by square underscore sum divided by real n, and once that is done I get the sigma using this formula, and then it prints out the average value and then the sigma. So, once that is done, in the next part I compute the correlation function. So, if you refer to the lecture notes, the correlation function is given by it again involves a sum over n, and that is what I am doing here, and this part of the code computes this correlation function, and this now I am using q number of using a different set of random numbers to do that, and then again I use the same set and to write the data in such a way I plot I versus I plus 1th random number, how the plot looks like. So, that is what is my scatter plot. So, let us compile this. So, it is done, and then if you do ls minus ltr, we have this executable to run it. So, we run this. So, let us start with a very small set of random numbers, say 10. So, we know that the average value of a uniform distribution is 0.5 and the standard deviation sigma is 0.2886. So, let us see what values we got. So, you see with 10 random numbers here, the value of the mean is quite far away from 0.5. Similarly, the standard deviation is also quite far away from 0.2886. Now, if I increase the number of random numbers, say from 10 I go to 100. So, you see it is still away from, both the values are still away from the exact value. Now, we make it say 10,000. Now, you see it is slowly gradually going towards 0.5 and this is gradually going towards 0.2886. Now, if I increase it further, so then you see it is much closer to that value. So, it is taking time because it is computing the correlation function also. Okay, now let us look at what happens to the correlation plot. So, let us do it with first say 10,000. So, if I run it, then this is the data is stored here. So, you can use any plotting software you want. So, in my machine I have XMGrace. So, I will use XMGrace to plot it. Okay. So, this is what my data will look like. So, if I instead of, if I put the just the symbols here along with the lines. So, at k, so in the x axis I have k and in the y axis I have c k. So, for k equals to 0, it is nothing but the autocorrelation and it should be 1. So, you should expect a point here and it is somewhere which is close to 1. The reason it is not going to 1 is because the number of points are very few. Now, let us try to run it again with a few more points and see how the things are changing. So, what we do here is, so instead of 10,000, so rather than that, so I put 10 lakhs point and let it run. So, once it is done, what I will do is I will plot it in this one only. Let me try to plot it in this graph. See, it is done. So, let me just try to reload the data. Okay. Okay. So, the two things to notice here. Okay, let me just put some, make this 25. So, the two things to notice here. So, ideally if there is a completely random, the numbers are completely random, you expect the correlation to be 0. So, what you would expect is that these numbers, these plots will hover around 0. But when we have used fewer numbers for the correlation plot, what we see is that it is having a certain non-zero value. And the moment you increase the number of random numbers that goes into the evaluation of the correlation plot, you see that it starts hovering around 0 nicely. So, this also tells you another thing, that in addition to that in these type of methods. So, what is also very important is the average. So, one needs to do a very good average, by good average I mean average over sufficiently large number of points to get into some meaningful and realistic number. Now, we will also look at the scatter plot. So, for the scatter plot what we will do is we will use fewer random numbers, so that you can see. So, let us put say 10,000 random numbers and do the evaluation. So, let us open it in XMGrace. So, if your numbers are correlated, then what your scatter plot would have looked like Okay, let me just first make this plot proper. So, circle, let me reduce it slightly, straight line I do not want, I just want to see the dots here. So, this is how it, you see it is, I mean the points are spread all over this area, from the x axis is from 0 to 1 and y axis again is from 0 to 1. Had there been correlations, then what we would have seen is that certain parts of this area is covered, while the other parts are empty, or it would have been something like a diagonal one. So, this says, since in all the points are scattered all over the space, all over the extent of my plot, this tells that the numbers are not correlated and it is genuinely a good random number. There is one more test which I am not going to show it to you, and I leave it to you as exercise. That is, what you can do is you can generate say 1,000,000 random numbers, divide them into small bins, and once you have them in small bins, you can plot a histogram, that is, in each bin how many random numbers are there. So, and what you would see is that the height of the histogram and of all of them are same. That is what it tells you, that it is a uniform distribution, because each random number has an equal probability of there is an equal probability of finding each random number in a uniform distribution. So, if you use very few random numbers in plotting the histogram, then you may find that some bin heights are larger, some bin heights are smaller, but then gradually as you increase the number more and more, as you increase the more and more random numbers, that is, as you enhance or better the sampling, what you will find is that the heights of all the bins are same.